Welcome to the course UEC 001. In this module, we discuss about the various analysis method for the P injection diode. So let's start with the graphical aspects to solve the problem. So as over here is biasing supply, and suppose I'm having a load resistance of value RL. So this is my load resistance RL, and I'm interested to find the load voltage VL across the load resistance RL. Voltage across diode is D, and suppose this is my diode D. External supply VI is connected over here, and as you can see that positive terminal of supply is connected to the P side of diode and negative to the N side of diode. So this diode will be forward bias, and after that, if I'm saying that the current flowing through this particular diode is current ID, then we can apply KVL and we can find the diode. So drop across the diode is VD minus drop across this load resistance. So ID into RL. This equals to 0. So this is my KVL equation and we can rearrange it. My input voltage VI will be equals to VD plus ID into RL. Now for this equation, this is the equation of a straight line equation. So in order to draw the load line on this curve, I need 2 points, and by joining these 2 points, one can easily draw the straight line. Okay, so in order to find the 2 points, what we can do, apply the basics of high school level. First, put value y equals to 0 and find the coordinate of x. Then do the reverse part, put the value of x equals to 0 and find the coordinates of y. Okay, so over here, considering if vd equals to 0. So when vd equals to 0, that means we will have vi equals to id into rl. Ultimately, my id will be equals to vi divided by rl. So I can say that in this situation, I am having a point 0 and vi upon rl. Now the second case, if I am considering that value id equals to 0. So if this condition hold, I will have vi equals to vd directly. That is, my vd will be equals to vr, and the second point will be vi and 0. So I can easily draw a line by marking the points. So for the simplicity, I am first joining the line, and this is my q point, point of operation. This is my q point, which is line intersecting the curve and these 2 points. So it is my vi upon rl, and this point is my vi. So I can easily find the corresponding values of idq, and this is vdq. This is my load line. So as it is including the load resistance and the input supply vi, so termed as load line, and doing the analysis at this q point, which is the intersection of load line and the characteristic. So corresponding, I will have idq and vdq. Okay, so the next topic is series and parallel combination of diode. So under series combination, let us consider a situation. Suppose there are two diodes, diode D1 and D2. They are connected in series fashion, and suppose one load is also connected. This is my load. So in order to the proper functioning, my external supply E, suppose these are two diode D1 and D2, and their junction voltage is suppose VD1 and VD2. This is my load resistance RL. So for the functioning, external voltage, this E should be greater than and equals to VD1 plus VD2. So if this condition satisfied, E is greater than or equal to VD1 plus VD2, then you can see that diode D1 and D2 both are forward biased. However, if this condition is fails, if E is less than VD1 plus VD2, then insufficient voltage is there. Therefore, D1 and D2 both will be off. Both will be off. Okay. So I'm saying that this is my case number one and this is my case number two. So for case number one, the behavior of circuit, the circuit will be like this. It will replace by a battery of value VD1. This is also replaced by a battery of VD2 and load resistance is there. In fact, in this part, if I am interested to find the current flowing through this particular loop, so this is my E plus minus, this is my VD1 plus minus, this is my VD2, and this is my L. And suppose I am interested to find this VL also, voltage across this load. Okay, so I can apply KVL over here, apply KVL to the loop. You can understand this loop. So it is E minus VD1 minus VD2 minus I into RL equals to 0. Okay, so one can easily find the value of this I if VD1, VD2 and RL is given. So I can write the value. Current I will be equals to simply E minus VD1 minus VD2 divided by load resistance RL. And if I want to find this value VL, so this will be simply I into RL, or this can be calculated as E minus drop across this. This will be simply E minus VD1 minus VD2. So this is the analysis and the series connection of the two diodes. So this is series connection of the diodes, and this is for case number one. However, for case number two, let me draw the circuit. Both will be open as I am having this condition. My E is less than VD1 plus VD2. So this is my E. This is the second case. In fact, this is also a series combination. Okay, and I am interested to find the current I, but with the fundamental concept of electrical engineering, I will be here equals to 0 as no current can flow through the open circuit. So value of VL will also be 0 because the value of I is 0. Okay, and that's it. So this is the second case. Okay, so this is my series combination, and let us discuss one more issue. So this is the direction, how the direction of diode is connected. External batteries E, diode D1, diode D2, load resistance RL. Now this is the interesting part. You can check the anode of first diode D1 is connected to positive terminal of battery, and cathode of first diode is connected to the cathode of second diode. Okay, So in this situation, diode D1 uh, will become forward bias, but as the positive terminal through this diode connected to the cathode of diode D2, so my diode D2 will be in reverse bias. Okay, so the equivalent circuit of this is, it will be an open circuit, and let me draw the case. So I'm considering that both diodes are ideal, so it will be replaced by a short circuit. I'm saying that both are ideal, and second diode will be open circuit. So now you can imagine about the current flowing through this loop and the voltage across this load resistance. And I think you must have the answer. Value of current I will be 0 and voltage VL will also be 0, as no current can flow through the open circuit. So this is another case of my uh, series combination. Now let us discuss parallel combination. So suppose this is my resistance R, external battery E, diode D1 and diode D2, and I'm saying that both diodes are made up from silicon. I'm saying that both diodes are made up from silicon. So first thing, you can check both diodes have been connected in parallel configuration. So if I am saying that the voltage, external voltage E, if my voltage E is 0.7 volt, then both diode will be on and my equivalent circuit will be like this. External battery E, and I have taken this term. So this is my parallel combination case and this is my equivalent circuit. Okay, so one can do the analysis, can calculate the value of this current I, how much current are flowing here and how much current are flowing over it. Okay, so one can easily calculate these. See this configuration. Again, both diodes are connected in parallel configuration. Resistance R, E. I'm saying that both diodes are again made up from silicon. Similar value, diode D1 and diode D2, and sufficient input voltage is available, means this condition is still hold. So now you can check what should be the equivalent of this. What should be the equivalent of this? Now you can check anode of D1 is connected to the positive terminal through this resistance, but cathode of D2 is connected to the positive terminal. That means diode D1 will be forward bias and diode D2 will be reverse bias. So whosoever is forward bias will be replaced by an equivalent battery of value 0.7 volt, as it is made up from silicon. However, this will be replaced by an open circuit. So the E, this is my resistance R, plus minus 0.7 volt. Suppose I am having an external battery E and this is a positive battery. And now I'm using two diodes connected in parallel, taking another diode, one more diode. So let us try to find the combination of series and parallel. This is load resistance. Suppose resistance R, diode D1, diode D2, and diode D3. And say, suppose diode D1 is made up from germanium, diode D2 is made up from silicon, and diode D3 is also made up from silicon. So what will be the now interesting part over here is you can check two diodes of different material. Diode D1 is made up from germanium, D2 is made up from silicon. Both are connected in parallel and their cut-in voltages are different. We know that the cut-in voltage of germanium is 0.3 volt and cut-in voltage for silicon is 0.7 volt. Okay, and we know the fundamental concept of electrical engineering. In parallel combination, voltage will be same. So it will not possible that both diode will be conducting. So out of these two, only one will conduct. And which one conduct, that we have to investigate. Okay. So for the better understanding, I want to show you the VI characteristic, including both diodes on a same graph, ID in terms of milliampere, VD in terms of volts. This is the curve for silicon, and this is the curve for germanium. That means somewhere I will have value zero point 0.3, somewhere I will have this value 0.7. Now you can check in this forward bias case, when I am increasing the voltage, from 0 to zero point 0.3 level, you can check at when I will increase the input voltage 0.3, then you can check the voltage across the circuit is almost constant, and it is somewhere near the zero point 0.3 only. So even though I am increasing the external voltage, but the effective voltage is constant, so it will never reach the zero point 0.7 volt. Okay, that means this diode will never receive a voltage greater than zero point 0.3 volt. Okay, so intuitively 0.3 volt. That means the equivalent circuit is like this. It will be replaced by a battery. However, this will be open circuit, and then it will be replaced by a battery. It will be forward bias because we have already taken that sufficient input voltage was there. So this was R. It will be replaced by a battery of 0.3 volt. This is 0.7 volt, and this is my off. So I'm marking over here. This is off as it is reverse bias, on as it is forward bias, on as it is forward bias. Okay, so this is the situation. This is very interesting problem. Suppose what will happen if more than two diodes have been connected in parallel configuration, then we have to check whosoever having low cut-in voltage will be conducting, will be on. Now let us discuss one numerical. So let us see for this problem, we have to determine current I1, I2, ID2. If this information is given, I can check sufficient voltage is given, 20 volt external supply is given. So let us find the equivalent circuit. So as the anode of D1 is connected to supply 20 volt positive terminal, and then anode of D2 is also connected to that. So both diode will be forward bias and replaced by a battery of 0.7 volt. So first let us determine the value of current I1. Let us determine the value of current. This current will be 0.7 divided by 3.3 into 10 raised to the power 3, 212 milliampere. And now apply KVL to this loop. Now I am applying KVL to this loop. 20 minus 1.4 divided by 5.6 raised to the power 3. This is my current I, 3.32 milliampere. I am considering this is node A and apply KCL at node A. So we will have current I2 equals to ID2 plus current I1. So current ID2 will be equals to directly I2 minus I1, that is 3.32 minus 0.212, or it is approximately 3.11 milliampere. So this is a very interesting numerical. We have calculated all the currents which we need to find. So this is about this example. Okay, so this is the problem. There are two diodes, both are made of from silicon, are connected in parallel configuration, and suppose their inputs are A and B. and a load resistance R of 1 kilo ohm is connected. We have to find the output V naught across the load resistance R. And there are four options. So in case number 1, A is connected to 10-volt battery, B is also connected to 10-volt battery. Case number 2, A is connected to 0-volt battery, B is also connected to 0-volt battery. Case number 3, A is connected to 10-volt battery, B is connected to 0-volt battery, and the last case is A is connected to 0-volt battery and B is connected to 10-volt battery. So we have to find the output for all these cases. Case number 1. Now you can check 10-volt battery is connected across here and 10 volt across here. That means sufficient input voltage is available to make both a diode forward bias. So I am drawing the circuit for this case. Resistance R 1 kilo ohm, and I will have V naught over here. So this is 10, this is 10. Both will be conducting zero point 0.7 volt, zero point 0.7 volt. So what will be the output voltage? Now I have to check what will be the output voltage. So if you can take any loop, suppose I'm taking this part as a loop. I can take either this loop or the second loop, then apply KVL. What I will receive 10 minus 0.7 minus, I can say that V naught directly, minus V naught equals to 0. Therefore my V naught will be equals to 9.3 volts. My V naught is 9.3 volt in this case. Okay, now let us discuss case number 2. Let us discuss case number 2 when both are connected to ground. When both are connected to ground. So V naught 1 kilo ohm, as both are connected to zero level or directly ground. So you can check no sufficient input is available. Minimum 0.7 voltage is required to make diode on. So my both diodes will be off. D1 and D2, both diodes will be off. And if these both are off, voltage drop across this resistance because there is no loop. So drop across this resistance will also be zero. That means in this case, my output voltage V naught equals to 0 volts. Now let us check case number 3. Let us check case number 3 over here. In this case, A is connected to 10 volt, B is connected to 0. So obviously the first one diode will be conducting and second one will be off. Okay, so quickly I am drawing the circuit. This will be off because this is connected to ground, this is connected to 10 volt, and this is zero point 0.7 volt now. 1 kilo ohm. I want to measure output across here, and now you can check there is one closed loop due to diode D1. Okay, so suppose this was D1 and this was D2. So due to diode D1 there is a closed loop, and I can apply KVL. It will provide me 10 minus 0.7 minus V naught equals to 0. Therefore V naught equals to 9.3 volts. Consider the last case now. In last case, what you can observe, A is 0, B is 10 volt. That means now D1 will be off and D2 will be on. Okay, so as this terminal is connected to ground, that means first diode will be off and second one will be conducting. Now I will make output across here. So this D1 is off, D2 is on, and it will be a value of 0.7 volt as 10 volt was connected here, 1 kilo ohm. So with the similar terms, I will have V naught equals to 9.3 volts. Now this is a very interesting outcome. Now you can check. Let I'm saying logic 1 is defined with a voltage of 10 volt, and logic 0 is defined for a 0 volt. Okay. Now you can check for the all these cases. For all these cases, I am output V naught, and my A and B, these are the inputs, and this is my output. This is very interesting relation, in fact. And you can check now. I'm writing the value of inputs in terms of these logic. So first one is both are 1 1, second logic both are 0 0, third logic 1 0, and the last one is 0 1. And interestingly, if I'm approximating 9.3 is also that it can be come near, very near to this level. Okay, so I'm approaching that 9.3 level can also be belonging to this logic. So you can check for the first case, when both are at 1 1 level, my output is also 1. When both are off condition, my output was 0 and 1. Any one is at 1 level, then output is 1. And you can check, if you can recall the high school level physics, then you can. So this is my OR gate. So with this example, you can see that you have seen how we can design OR gate with the help of diodes. Okay, so this is another application of the junction diode. Okay, so thank you.